hear me. OK. So yeah, you can hear me, you can see me, because it's like, if I'm covering the slides, let me know, because I'm quite tall. So I'm Javier Ramirez, that's my Twitter. And I'm one of the founders of Tiawaki. We are just a two-people company, and we help others work with big data, with cloud, especially with the Well Cloud platform, and with distributed systems. And that's what I'm here, because I want to tell you not about my company, but about distributed systems, how they work, how distributed databases are built so they can be always on, even when there is a disaster on a data center. And we are writing code, and code runs on machines, and machines are on data centers. And if you have like a regular application and it's running on a machine on a data center, and there is an earthquake, like it happened on IBM in Japan a few years ago, and your machine is in one of those servers, probably your application stopped running. If it didn't stop running, because some of the servers were still running, probably the network to the users is not working. So your application is not working anymore. And it's not only about earthquakes, because also thunderstorms. Just last year in Google in Brussels, one of the data centers for the cloud platform, in a thunderstorm, not only one lightning, but 4 lightnings hit the, yeah, I know, hit the data center, and some data were lost. So if you have like a conventional database, a conventional application, you have just a single copy of your data will be lost. And I don't like that. It's not only about earthquakes or thunderstorms, it's also about the cloud itself. 3 years ago, one of the Facebook responsibles of data centers get a call. Hey, we have a cloud inside the data center. It's like, yeah, of course, we have a cloud in the data center. It's like, no, you are not understanding me. The air conditioning is condensating the air. We have a cloud inside of the data center. It's raining on the servers, and we are having a problem here. It's like, OK. So these are the kind of problems that, that you can have on your data centers. Or just chipmunks, squirrels. They are fun. Wow, they are so cute. Until they start gnawing on your cable. And then, you are losing half of the capacity of your data center in Yahoo. It's like, oh, yeah, I didn't count on that. And that's why when companies are laying cable underwater, they put Kevlar around so the sharks won't break the cable, because that happens all the time. So the internet is a dangerous place. But one of my favorite stories of connectivity issues is between Georgia and Armenia, which are like these 2 countries here. So you see, they have a border, and this woman, for a few hours, she was like the most wanted person in Armenia. Because, she's a poor woman, she was like trying to get copper to sell it later, and when she was like digging, she accidentally broke one of the cables, which is bringing the internet to most of Armenia, and Armenia was without internet for almost the whole day because of that. If you have your database, your system, running in that data center anywhere in Armenia, then you are out of luck. And it's like, oh, yeah, but these are isolated incidents just for fun. Of course, they are isolated incidents. Just past year, all these providers, small names, had some problems with the data centers, all of them. And of course, if you are running on Rackspace, DigitalOcean, OVH, any provider is sending you emails. We have like a scheduled maintenance. Your servers are not going to be running on Saturday. On Saturday, I want to be taking care of drinking, sleeping, watching Netflix, playing games, whatever. I don't want to be like, oh, is my server on or off? It's on. I don't want to be worrying about that. But, the thing is like data centers are a complex thing. And complex systems are going to fail for many reasons. Some of them are I was going to say funny, earthquake, I don't know. Some of them are like curious, like the one I just mentioned. But others are like, for example, delivery truck hits a wall and breaks some servers. That happened to Rackspace. It could happen anywhere, and malicious hackers, political incidents, software mistakes. You deploy to production, you break the network. It happens. Human errors. Mechanical failures, disk are going to break, electric failures. So data centers are going to break for sure, no matter where you have them. And it depends how important it is for your business to be always up and running. You should be considering not having your data on a single data center, but distribute across several of them. For example, another example for the business. Last year, 2 years ago, for the whole morning on United States, Starbucks couldn't sell coffee because the point of sale terminals couldn't connect to the servers. For the whole morning, in the whole of the US, Starbucks couldn't sell coffee. Some shops closed, others were like giving coffee for free. You know, for the business, they were not happy. No, you don't want to be the software guy who caused that problem. Or even worse, on Tinder, last year, a lot of people losing their Tinder matches for almost the whole day. They were desperate. How am I going to lose my virginity now? You know, my matches, where did they go? And that's so it really, you know, yeah, it didn't happen to you, but I was like quite worried for a few hours. Thing is, I had to try distributed system. It's not, I mean, yeah, it's a hard job. So the thing is, if it's important for your business to be always on, you should be distributing your data. And as a bonus point, if you distribute your data, in many cases, it's going to perform better than a centralized solution, and it's going to be cheaper, because you are going to be able to use much cheaper hardware than that building like a huge mega computer that can hold the whole of the internet. It doesn't exist. So you better do something for that. And you can tell me, OK, I wouldn't lose my data because I'm already distributing data. I have a copy. OK, that's distribute data. It's not high availability. Because, but still, if you have a backup, first level of distribution, that's OK. You are good enough. Just don't be like Vodafone. Don't keep the copy in the same building as the main data store. That's wrong. If you have a fire and you lose 1 year of data, it's not going to look good in your CV. And you are going to need your CV if that happens. So, so that's the first thing. But if you want to have like a replicated system with some kind of high availability, then you can use like replication, master-slave, which is like the most basic level of distributing data. This is the way for the last, 30 years, databases have been working. So the way this works is you have like a master server, a central server. All the updates, all the insertions, deletions, whatever, go to the master server. And then the master server is going to replicate them on the replicas, on the slaves. The way to do this is like the master server, every time there is like a write operation, is going to be kept in something called the binary log or the write-ahead log. So every time there is like any insertion is going to be kept there, and we're going to replicate that log to all the copies. So each replica is going to replicate the same instruction, so it's going to end on the same status. And that's how it works. And it works perfectly, flawless. It's not only for relational databases. Some interesting NoSQL databases, like Redis, for example, if you are not running a Redis cluster, just a master and a slave, they work exactly the same. And it works, and it's quite cool. But it has a few problems. One of them is like, as you can see, all the operations have to be replicated on all the servers. So if you have like a medium-sized installation, like for example, Netflix has like 1,000 servers only for the Cassandra database. If you have 1,000 servers, running all the operations on 1,000 servers doesn't look too optimal to me. And also, apart from running on all the servers, you are going to store the whole database on all the servers. It's a lot of space that you are going to be using. Replication is quite cool if your challenge is that you have like a lot of people reading data. But if you have a lot of people inserting data, that doesn't scale. If there is a network problem, you cannot continue using the system as usual. And the master server is a single point of failure. Yeah, you can always let a new master and so on. Still, it's not ideal. So next level of replication, the multi-cluster, the master. All my servers are awesome. All of them can accept like as many writes as you want to throw to me. So if one of them is not there, I'm not going to notice, because I have all the others. That's cool, that's cute, I like it. So the way it works is like you can write in all the servers, in any of them. And all of them are going to have their binary log. So every time there is an insertion, they are going to send the binary log to everyone else. And they are going to replicate, and that's going to work. And that's more interesting than before. Because, I can scale already the writes up to a certain point. Because I'm going to have problems again. I still need to keep the whole database in all the servers with this model.
And don't say anything, OrientDB. I know you're looking to me now. But in this model, like the traditional way of multi-cluster, you have to keep your whole data in the whole servers all the time. For example, Facebook, they have over 20,000 servers only for data analytics. 20,000 servers only for data analytics. You don't want to have all that data replicated in all the servers in the cluster. You really don't want to do that. So that's the first thing, that all the operations have to be in all the clusters. The other thing is, if you want replication to be synchronous, then you have to wait until all the masters apply the changes. If the masters are very close to each other, because you only are planning for, hey, if this server goes down, I still have this other, that's cool. If they are in another continent, the latency is going to be too high. So, if you want to have like everything consistently, your system is going to be slow to use. If it's not consistent, if it's asynchronous, then you have to deal with conflict replication. And most masters are not traditionally very good at, at dealing with conflicts. People are doing like new things with multi-cluster, and they are starting to do like sharding, and they are starting to do like different things. And that's basically the things I want to tell you in a moment. So what if? What I want is a system which is like always on. I can always write or read or delete, even if I have an earthquake and a squirrel and whatever. I want to have the system like always running. I want to be able to scale both writes and reads, and I want to be able to have data distribute, not all in all the servers, just a few parts of the data here, parts of the data there, which should be much better. I can run it on the chip hardware, and also diverse, because if I have 1,000 servers, or 70, or 10, I don't want to have the 11th server exactly the same as the others. Because probably I want to have like different configurations. So I would like to have a system that allows for me to have like slightly different servers, and it's still going to be running. I want the system, this is my wish list, so I can ask anything I want. I want my system to run locally to my, as close to the user as possible. So latency is very low, so the impression for the end user is much better. And since I'm asking, I would like the system to be able to add capacity or decrease capacity if I have more demand or less demand, because we are not in the 80s. I don't have to have just 10 servers and keep them forever. I can just grow and shrink as I need it. So this is what I need. And the good news, this is possible today. The bad news, I have to forget about many of the things that I've been used to. Because, when you are studying or when you are working, you get used to this like cute relational database. Because a relational database, really, they are truly awesome. You can create like 10,000, you can create like 200 tables, and then you can do a query, joining the 200 tables, adding filters to each of the different fields, sorting by all the filters. It's going to take forever, but it's going to work. So, relational databases are awesome. And you have things like transaction, and you have like a lot of things that are really interesting to have. When we are dealing with distributed databases, a few of these things are not going to be available. Your queries are going to be simpler. You are not going to have as much power as with SQL. You probably don't need it if you plan ahead. Because the thing with SQL, most of the time, you don't really plan how you are going to be querying the system. You only plan which are your data and normalization and these boring things. But the thing is, with distributed databases, you can do also interesting things, just not as powerful queries. Transactions, in many cases, are limited. So, you have to be a bit careful with that. So that's what I want to tell you about. And I think I'm doing fine with time. That's what I want to tell you about. I want to tell you how distributed data stores work, how they are designed internally to be able to do all these things I've told you like 2 minutes ago. Before I tell you how they do it, I'm going to tell you a few of the names, because if I ask you about relational databases, you probably know all the names. You know MySQL, Postgres, SQL Server, Oracle, SAP HANA, SQLite, I don't know. There are a lot of providers, and you probably have played already with a few of them. But if I ask you about distributed data stores, you maybe don't know the names, but you do, because there are already a lot of providers. This is just a small sample that support distributed data. So Amazon Dynamo, Google Bigtable, Voldemort for LinkedIn, Apache HBase, Riak. MongoDB is not here, but it could be here, MongoDB too. They also have like a fantastic cluster. Couchbase, Google Spanner, Redis when it's running as a cluster, Cockroach, OrientDB. So there are a lot of players already here. And all of them are different. They cover sometimes slightly different use cases. They have different capabilities. But all of them, when you design a relational, when you design a distribute the data store, you need to be thinking about the same kind of problems. So for the next 20 minutes, what I'm going to do is telling you how you can think and how some of these databases are solving these problems, which is how I distribute data. If I don't want to have the whole data in all the servers, how I choose which data I put where. And if I don't want to lose data when there is like a problem in one of the data centers, how do I keep several copies? How do I do replication? And durability. If a user is inserting something, and at that moment something goes wrong, how can I be sure that that data is going to be kept? If I have conflicts, and I will have conflicts for sure, how can I solve the conflicts? If I have like a large cluster, and I'm going to be adding and removing nodes, how do I know which other servers are part of the cluster? Are they working or are they not working? And when there is a network partition, so when I cannot communicate across the servers, how the system is going to work? And, am I going to be able to add and remove nodes? So all these questions are the questions that these systems have to think about. Some of them will not cover all of them. Some of the systems will say, you know what, I'm not going to offer this one. But still, it's something that you have to be like thinking about. So first thing, data distribution. That's really easy, really, really easy. Because it's like, OK, we have like a huge data set, and we want to send some data to one server, some data to the other. We could do something very easy, like everything started with an A goes here, everything with B goes here. So in truth, it's something very similar, but we apply a hash function. So what you do is like you apply a hash function to you have always like a key. A key can be a column, 3 columns, whatever. So you take the key, you apply a function, the function gives you a number. Everything with the same number goes to the same server. For example, here's like this is taken from the Amazon documentation. So for example, here you have, this is an abstraction that you will see very commonly in distributed systems. You have what is called a ring. So you have the ring. In this case, I have like 32 possible values from 0 to 31. So I'm going to have a hash function. And for each key that I pass, I'm going to get a number between 0 and 31. Everything which is in 0 is going to be in this partition, 1 in this partition, 2, 3, blah, 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 blah. So if you tell me the key, I know where to store or where to read from. That's easy. Second part. I'm going to assign partitions to servers. If I have 4 servers and 32 partitions, each of these servers is going to be taking care of 8 partitions, fairly easy. So, you can add more servers, but the logic is still like very easy to. If at some point something is not easy to understand, you can throw me something or tell me or whatever is more convenient. But at the end, we can also have questions. So, partition is not really that difficult. But with partition, you have only divide the database in small parts, which is not bad because if your database is huge and you need to run a query across a huge disk, that's going to be slow. If you are going to run the same query across 10 disks at the same time, it probably is going to perform not 10 times faster, but probably 8. So just by dividing data, you probably are going to make the system faster because you can parallelize things that you couldn't do before. That's interesting already. Still, if I only separate the data, I could lose information. So I will need to replicate also the data to have several copies. So if one of the servers goes down, I still have at least a copy. How we do this? Well, you don't want to have at least a copy. You want to have at least 2 copies. Because imagine I have 2 servers, and one tells me A. I tell one server, which is the data for the key A? It's like 1. Which is the data for the key A? 2. Which is right? I don't know. So if I have only 2 copies, it's going to be difficult for me when I have like any corruption to know which one is right. If I have at least 3 copies, I can always say, hey, you know, I have a quorum of 2 against 1. You are the loser. So, you know, you want to have at least 3 copies. And there are a lot of strategies for this. A possible strategy is the one you are seeing here. It's like, if I have a key that should belong to this node, I'm going to replicate this key. For example, Cassandra was like this, or used to work like this. I have a key for this node. It will be in B. I'm going to store it also in C, R, in D. If I have a key for E, I will store it also in F and in G. So that way, I always have 3 or as many copies as I want of my data. So it's replicated. It's also, you know, in real life, it's not as easy. It really depends. In open source, it's usually that easy. Then the commercial version has the capability to work across data centers, and replication is done also depending on geolocation. So your 3 replicas don't end up on the same server or on the same rack. So they are going to be at least in different racks in the data center, or probably in different parts of the world, which is much better. So, you know, but the concept is this, is just how complex you want to make the replication algorithm. So that's interesting. We already know how to divide the data, and we know how to copy data in different nodes. So for a particular key, I know exactly where it's going to be. We are already getting there. But now, imagine I am the user, and I'm going to be writing data into, someone didn't let the talk, sorry. So I'm going to be writing data into the store. At the time I'm writing the data, at that moment, you know, I had the earthquake. So the server didn't have time to replicate to the others. What happened with that? Well, yeah, there is an earthquake, people are dying, so I don't really care about the data. But still, you know, maybe it was like very important data or something, like a like on Facebook. So, you know, I don't want to lose that. And yeah, so now the likes in Facebook are quite cool because you can say like and put like a sad face, so it's quite interesting. Anyway, how can we make sure that we are not going to lose that data if the server fails before replication started? That's called durability. So how we make sure when I'm writing data, that data, when I can be sure, the data is going to be stored for sure. So to make sure it is going to be written for sure, I need to wait at least until one server tells me it's written. And when the server tells you it's written, it might not be on disk. Because, you know, in operating systems, they have a buffer. So when you write something, they tell you, yeah, it's in the buffer, but it's not really, it's not on disk. So, you know, but you need to have it at least on 2 servers to make sure that, you know, things are going to be failure-free. So this is called the waiting quorum. Many of these systems, you can configure in how many servers has to succeed the replication before the system considers it went well. So if you tell me, you know, I want until the data is not at least on 2 different servers, the insertion wasn't successful. So if a client is sending me data, and I get the data on the server replicates to another. If I'm replicating to another 2 servers, by the time I know the data is in the second server, I can already say, hey, OK, everything went well. If after a while I get the timeout and data wasn't replicated, it's because I'm failing. I cannot connect to the others. I'm going to remove this. So, you know, we're going to return, hey, it didn't succeed. So that's the writing quorum. And you probably can configure it in your system. And for some data, maybe you don't care because it's a Facebook Live, because it's a cache, because it's something. So sometimes you can say, hey, I want to be like really performant on inserts. I don't care if I'm losing data. As long as one server tells me that's fine, that's fine. Or the other way around. Maybe something is very, very important, and unless everyone tells you it's commit to disk, you don't want to, you know, to continue. It could happen. You wouldn't be highly available in that case because, you know, but it could happen. So usually you can have like a quorum for reading and also for reading, because when you read, you can have the inverse problem. Someone is sending data. I'm reading from the replicas. How can I know the replica I'm reading from is not the latest one the last one getting the update, and it's still with the old data? In most of the cases, I don't care. I don't care if you hit like now, and I see it 2 seconds later. but sometimes I care. So you can also have like a read quorum. So you can be sure the information you are reading is as fresh as possible, because it's coming not for a single server, but for several servers at the same time. So that's how you get durability. And you can usually tune how much durability you want to do. In some cases, you can even tune it by operation, which is quite cool. But with this kind of thing, we will get conflicts. Because we have like different servers, they are replicating to each other, the networks are flaky, they are going to be failing. Even if there's not a catastrophe, networks are something that is not reliable, are going to be delays. So I'm going to see conflicts. Like for example, this has happened to us all the time. I delete something, I reload, it's still there. After 2 seconds, it's not there. What's here? And the other way around. I insert something, I cannot see it. Oh, now it's appearing. So these are conflicts. Or something should be unique, it's not unique. I have like different values. When I reload, 1, 2, 1, 2. Eventually, I see it. This happened, for example, with DNS. You change the domain name, and for a while, it's like you are asking everybody, hey, check this URL. What are you seeing? What are you saying? I still see this. I see the other thing. Eventually, everybody is going to see the same thing. That's what's called like eventually consistent. In the end, everybody will see the same thing, but for a while, you are not going to be saying the same thing. So these are conflicts. And how we solve the conflicts? Well, one strategy is just ignoring the conflicts. I decide that my system is not going to have conflicts. For example, if every time we get something to write, we use like quorum-based algorithm like Paxos, like Raft, in which like a lot of servers have to agree on the value before they tell me. Not only that I say, hey, at least 2, but between them, they have to make sure there is a majority of the servers that have the value, and when the others are available, they are going to replicate. Then in that case, you are not going to have conflicts, because there is always someone which is like the master, and it's going to tell you, that this is right. The challenge with this is it has a lot of latency. And in distributed systems, if they are like distributed across different continents, it might be very bad latency. So generally, distributed systems don't use this kind of thing for everyday things. They might use it for things like membership of the cluster, for those things, but not for everyday data, because it tends to be slow. In general, some people are using them, but in general, no. Another technique is just, hey, I don't care. If I have conflicts, the last one doing the write wins. If 2 people at the same time are updating the same record, well, I don't care, last one wins. It's another very popular, it's much more popular than you could think, last write wins. What some people do, like for example, Cassandra used to do, is like they do very atomic writes on individual fields on very short time. So, it's difficult to have conflicts there. Still, these strategies are not ideal. So you probably want to have something a bit more flexible. And you can do conflict resolution when you are writing the data or when you are reading the data. In a lot of distributed systems, it's much more common to do the conflict resolution when you read the data. If you read data from, as I told you before, a quorum of at least 2 or 3 servers, and the 2 of them tells you the same data, which is what happens 99.99999% of the times, that's fine. But what if one is telling you A and the other is telling you B? Then there is a conflict. How you solve conflicts? Well, there is a technique that you probably, most of you know the name, some of you don't, but if you are using Git, you are using Git, yes? If you are using Git, you know how it goes. Because vector clocks is a technique for this. In Git, when you have a branch which is like everything is one commit after the other, there is never a conflict. A conflict happens when you have a commit coming from 2 different parents. That's a conflict. And then you have to fix the conflict. So vector clocks is a way of working with this kind of data. Basically, what we are doing is every time we insert data into the system, we don't insert only the data. We insert also the history of which servers and in which version they were storing data. So for example, I have here a data, and so the first time is storing the server X, and the server X says, hey, this is like the version commit, if you want, number 1. OK. Next time, the same server is like, in the same server, I'm just going to increase the version. There is no conflict. It came from me. I was the last one inserting this, so there is no conflict here. And here we have 2 servers processing this data in parallel. So this one is going to say, I'm going to change this data to 3. And the history is, I took it from the server X with version 2. I'm adding this version for my server. And this one is going to say, I took it from server X in version 2. I'm going to add it with my version. When next time we are reading, we are detecting there is a conflict, because we can see the history of the data of this branch and this one is not the same history. So they are coming from divergent frames. Thank you, 10 minutes. So they are coming from divergent branches. And then I have to fix the conflict. It's exactly what you do in Git. So this is how it works. And the client in this case is going to have to decide if the conflict can be fixed. Often it can be fixed because, if it's the same record but on different columns, you don't care. That's not a conflict. If it cannot be fixed automatically, then you have to give an error, do reconciliation, do interesting things. So that's one of the things that distributed databases have to do for you, how to deal with conflicts when there is a conflict. And sometimes you can configure how you can deal with this. We already know a lot of things. We already know how to distribute data, how to make sure it's durable, how we deal with conflicts. But I haven't talked about the membership of the cluster, which servers are part of the same installation. And one way will be I keep a central list of servers with the names of everyone. That's cool, but central and distribute really doesn't match. And it's not going to scale if I have, as I said before, Facebook, 20,000 servers, so over 20,000 only for analytics. It's going to be very difficult to keep that centralized list up to date. It's going to add a lot of things. So we are using something called Gossip, which is like what we do with our friends all the time. It's like, imagine I ask my friend, hey, have you seen Peter lately? No, but Charles told me he saw it 2 days ago. So I know Peter is alive, or I know he was alive 2 days ago, because a friend told my friend that he was alive. That's gossiping. That's gossiping. And that's how these infection-like protocols work. They are asking each other randomly, several times per second. So what you do is if you are a server, you pick any random server, and you say, hey, what do you know about the others? I know this. And they'll tell you, and what do you know about the others? I know this. So several times a second, you ask different people. And even in a huge cluster, in about 2 seconds, you can get up to date in who is a part of the cluster, if they are alive or if they are dead. It was like this. Imagine the server 1, and the server 0, this one, and the server 1, this one. And we have 4 servers in the cluster, 0, 1, 2, and 3. I have a gossip list, which is how many seconds ago I talked to the other nodes. With myself, I talked 0 seconds ago. OK. With the server number 1, I talked about 7 seconds ago. He must be alive. With the server number 2, 23 seconds ago. And with number 3, 25. And I consider that if after 20 seconds I don't know anything of one server, that server is dead. So I have here my list of suspicious servers. I think these 2 are alive. I think these 2 are dead. And I have here my matrix. It's like, I think this, I know that the server 1 thinks this, I know that the server 2 thinks this, and I know this one. And the same the other side. So we exchange information, and after this is what number 1 updated. It's like, hey, I had here 7 seconds ago, now I have 0. I know the server 2 is alive right now. And I thought this was dead, but he told me that he saw it 5 seconds ago. So yeah, I know he was alive 5 seconds ago. But he also told me he saw this 23 seconds ago, me 25. So 23 seconds ago, the 3 was alive. But now it's like, OK, I think these are alive, but I think this is dead. And we also exchange information. And this information, I see the number 1 has here information that number 2 also thinks this is dead. So when I consolidate everything, I have here 3 servers, more than half, think that the server 3 is dead. So I'm going to consider server 3 dead. And until someone doesn't tell me this server is alive, that server is dead. And that's how I know who is a part of the group at every time. I just gossip several times per second. That's what I do every day. So that's it. That's how it works. You have a background thread doing this. It's really, really, really fast. It works perfectly. And it's exactly the same mechanism you can use for incremental scalability. If you need to add a new node in the system, you just let that node gossip randomly with any of the others, and in a few seconds, boom, everybody else knows there is a new kid on the block. That's it. So when you go down or when you go up, apart from this, you have to do a previous step, which is the new server is going to take a look at the ring of the distribution, and is going to claim some parts of the ring. It's going to say, hey, I'm going to be taking care of partitions 2 and 3, so I'm going to be one of the replicas for these partitions. So it's going to ask for data from the other servers. When the data is replicated to this server, it's going to start gossiping, and it's going to start saying, I'm ready for work. And when one of the servers goes down, we do the reverse. If I go down, since we all know which the partitions you were taking care of, I'm going to say, hey, we need to distribute this data because we need to have at least 3 copies. So if the copy number 3 went down, let's replicate before another one goes down and we have only 1 copy. So that's how this works. So it's a bit weird, but it's not that bad. We are almost finishing. What happens if at some point I have a network partition and I cannot communicate with any of the masters, with any of the servers that are dealing with a partition, but I want to insert data? So we can do something that is called a hinted handoff, which is basically any server can accept data for anyone else, even if they are not the destination of the data. Even if I'm not taking care of partition number 2, if the client cannot communicate with any number 2 server, they are going to send it to me. So I kept the data, and I kept the hint. And the hint says, hey, I'm keeping this data, but it's for you, which is what happens when you are in the office and the postman comes and gives you a packet for your friend. So you keep it. And next time you see him, it's like, hey, this was for you. That's a hinted handoff. Very easy to understand. Very easy to understand. If your friend never comes, your desk is going to be full of packages from different people. So you need to have like an anti-entropy mechanism. So once in a while, you need to be consolidating these things. So they are like another set of processes that are going to be taking care of, hey, do I have like too many hints for people? Maybe I should communicate with other people, see if we can do something with this, consolidate different hints. That's anti-entropy, and that's quite complex. But just for you to know that you need that, because if not, it's going to be impossible to have like a system consistent even eventually, because it gets to a point in which it's impossible. Just I cannot do it. So it looks interesting so far, at least for me. I don't know for you, but I hope. But it looks interesting so far. It's like, yeah, a lot of mechanism, lot of interesting, hopefully, things. But what this means is like when I'm dealing with a traditional relational database, the client of the database is very, very, very simple. Just write data and read data. When I'm dealing with distributed systems, the client needs to understand the server, because the client needs to understand the internals of the system. It's not a black box anymore. It's quite tied to the server implementation. The client needs to understand if I'm going to be writing or reading a key, which is the server that is holding this key. If if a node is not available, which node is the substitution for this one? Or I have to decide if this data is going to be durable or not. By default, maybe I can have a default, of course, but I have to decide on these things. And in some cases, some solutions, they have like proxy in the middle. So the proxies are going to take care of this. So the client is still easy because someone is doing the dirty job. But in that case, you are adding latency to the system. So it's not everything magical. There are still few things that are there. But in exchange, now you know how these systems work in a way. There are other possibilities, but at least you have the idea, some of the algorithms, some of the ways that these systems used to be always on, to be able to partition data, to replicate data, to make sure data is safe before they give the response to you, to be able to run on cheap hardware, because as cheap as you want, you can divide data in a lot of small servers, and that's about it. Closer to the user, because when you distribute data, you can have servers across the world, not in a central cluster, and you can grow and shrink as you need it. So with this, I will finish, But maybe you are thinking, I would like to build a system like this. And you could start from scratch, but maybe not. If you like Java, there is an open source library called Netflix Dynamite. And if you like Node, there is something called Uber Bring Pop. These two libraries, what they do is they give you all the algorithms I've been talking about on a single library. So you can put any data store there. For example, Netflix did this because at the time Redis didn't support a cluster. So they put Redis and they put Dynamite on top so they could synchronize a lot of Redis with this system. And Uber is doing exactly the same thing. They have things in Node and they want to replicate. The good thing with this is you can install one or the other and you can start creating these things. There are other open source libraries that you could use, but these two are quite simple to understand and play with them. With this, I'm not scared of this woman anymore. So that's all I have. If you want more information, there are a lot of links on distributed systems there. And that's me. So thank you. And if you have any questions, I'm more than happy to answer.